Hello everyone. We are going to work on designing an adiabatic plug flow reactor in HYSYS. So this is the example which we will work today and see how we design an adiabatic plug flow reactor in HYSYS. Before I jump into the problem, I just want to mention its reference. This is adopted as an example 5.2 and the page is 227. This is the book is Computer Methods in Chemical Engineering, and Naif Gissam is the author for this book. So let's go to the workbook here. It says that pure acetone is fed into an adiabatic plug flow reactor at a mass flow rate of 7.85 kilogram per hour. The inlet temperature and pressure of the feed streams are 760 degrees Celsius and 162 kilopascal respectively. In a vapor phase reaction, acetone is cracked into ketene and methane. Choose BWRS as a fluid package. So this is our chemical reaction that is happening in this process. The reaction is the first order with respect to acetone, and the specific reaction rate constant can be expressed by. So we have the value of the A here, we have the value of the E, and we have two objectives. We need to calculate the conversion achieved using the reactor volume of 5 meter cube where the tube diameter is 1 meter. The second objective is we need to calculate the residence time for plug flow reactor. Let's go to HYSYS and see how we will work in this. So we have materials, the components are acetone, ketene and the methane. Let's add them. So we are in HYSYS now. Let's click on add, and the first is acetone. This is my acetone here. The second is ketene. Third component is methane here. So we have all three components available in our HYSYS. So we have acetone, we have ketene, and we have methane done. The second is, it is saying that we choose BWRS as a fluid package, and then you go to the fluid package in HYSYS, click on add and choose the fluid package. These are arranged alphabetically. So here is my BWRS. Once I click on this, the HYSYS is okay with this fluid package. The next step is I need to provide a reaction here because we are dealing with the reactor. So you click on the reaction and click on add, and then click on add reaction again. And in this reaction, this is a kinetic reaction here, and click on add reaction. Now you can close this window and double click on RXN, means reaction in HYSYS language. And here we need to provide all the properties of the reaction. So the first thing is we need to add all the components involved. We have acetone, we have ketene, and we have methane. Now in the next step we need to provide the stoichiometric coefficient. For reactants we have the negative coefficient because they are being consumed, and for the product we need to provide the positive coefficient for the products. So let's look on our problem again. In this problem we have acetone, which is a reactant, and the products are ketene and methane. This is my ketene and this is my methane here. So we can say that the coefficient will be -1 for the reactant, and we have +1 for the product and +1 for the another product. You don't have to type positive, but as my practice with the HYSYS for more than 10 years now, I use a positive sign with this. The next information is important in our statement. The reaction is the first order with respect to acetone. So how we tell HYSYS about this? So acetone is 1 here. This is indicating that this is first order with respect to acetone. These are 0, 0, and just make sure you have 0 on the reverse orders. And in the next step, we have the information that our reaction is a vapor phase reaction. So we need to provide this information to HYSYS as well. How we work on this? You just select your vapor phase here. Now one thing you need to make sure that acetone is selected as a base component, because our reaction is first order with respect to acetone. I will take you back and just mention this again. It is first order with respect to acetone. If there is a different definition, you can always choose the component list here, and you must have more than one reactant in that case if you have a different scenario. Now in the next one, we need to provide the values of our reactions here. This is the value of our A. Let me choose this color, and this is the value of my. So my A value is 8.2 into 10 raised to power 14. So you go back to your HYSYS here, and 8.2 into 10 raised to power 14. How do you tell HYSYS, or how do you input 10 raised to power? Just press E here and press 14 and hit enter. Now HYSYS will recognize that you meant to say 10 raised to power 14, and the next value is 2.845 into 10 raised to power 5 kilojoule per kilo mole. So let's provide this value here in E, which is the activation energy, 845 into 10 raised to power 5. And I just want to double check I have the right units here. Yes, it is a kilojoule per kilo mole. So as you can see, the time I entered my E value, HYSYS is ready for with my reaction details. So now you can close this window, and before going into the simulation, very important step which most of us miss, that is you need to attach this reaction to the HYSYS. Your simulation will never recognize this reaction unless you don't attach it to your fluid package. How you attach it to the fluid package? You just click on add to FP, select this and click on this, and now it is ready. As you can see that my component list is ready, my fluid package is ready, and my reactions are ready. Now I can enter into my simulation environment. So here I am in the simulation environment of HYSYS. So let's go to the reactor here, and this is my plug flow reactor. We have already covered CSTR in our last lecture. So I will close this one, and now let's double click on this. So for the inlet, let's say I call it as a feed stream, and for the outlet I called it as a product. This is again an optional. Let's say we have the Q energy here. And the next thing is, as you can see that HYSYS is asking us to provide a reaction set. You go to your reactions and click down and choose this set. If you have entered more than one reactions, just make sure you choose the right one. So I click on this. Now we have unknown dimensions for this, as you can see that with the HYSYS information. So you go to your rating here and go to your size, and here we enter our dimensions of the reactors. So according to our problems, the reactor volume is 5 meter cube. So this is my reactor volume, and the tube diameter is 1 meter. So let's enter 5 here, which is meter cube. Good. And my tube length is 1 meter. Now the time I enter my dimensions for the length, HYSYS will automatically calculate how much is the diameter here. If you have more than one tubes, you can enter them. Just keep in mind, plug flow reactor is a tubular reactor. At least it must have one tube in it. And as you can see that there is a void fraction value of 1. This is indicating that we don't have any packing in our reactor here. If you have any packing, you can always provide the fraction of that void here. And I can also take you here. It says that void fraction is specified as 1, which means no catalyst information is needed. So in our example, we don't have any catalyst involved in this reaction. if you have the catalyst involved, then you can always enter its values or in terms of the void fraction here. And just keep in mind, if it is a tubular reactor, there could be more number of the tubes. For now, this is only one tube because I don't have any information in my question statement. Now in the next step, you go to your worksheet, and here we provide the information for our feed stream. We don't have the information for our product stream at the moment. So let's see what is the information available. So the mass flow rate of my stream is 7.85 kilogram per hour. So let's enter this. So mass flow rate is 7.85 kilogram per hour. And the next information that I have it, the initial temperature and pressure of the feed are 760 degrees Celsius and 162 kilopascal. So let's enter this, 760 degrees Celsius, and my pressure value is 162 kilopascal. And then we need to provide the composition. As you can see that in my reactant, it's only one component, which is acetone. So my composition here should be 1 for acetone. And then you can normalize this, which means to say anything other than acetone will be 0, and press OK. And the last step is we need to provide our duty. Duty information is not given to you. So over here, I will say that it is 0. Now, one thing you need to keep in mind when I'm entering the 0 here, this is what is indicating that this is an adiabatic reaction. There is no change in the value of the Q. And this one I will prove you once my simulation is converged. And the delta P is 0 as well. And now as you can see that HYSYS has converged my plug flow reactor. And here we can perform some analysis. So this is my so let's close this. So this is my plug flow reactor, which has been converged now. So here we can perform some analysis. The first thing which I mentioned you already, as you can see that there is a change in the temperature in the feed and the product. However, as you can see that there is no change in the heat flow in per feed and the product. This is indicating that this is an adiabatic plug flow reactor. If it will be an isothermal reactor, what you need to do, you need to delete the duty here that you provided. You need to delete this duty, and you need to provide the temperature here, which will be the same temperature as a feed for the isothermal reactor, and then you identify how much duty is required for your reactor, and that will be isothermal, but we are not working on that for now. So this is these are my conditions of the products, and these are the conditions of my feed stream. And according to our first objective, calculate the conversion achieved using a reactor of volume of 5 meter cube. How you identify that? You go to your reactions and go to results. So we have 49.66% conversion in this plug flow reactor, adiabatic plug flow reactor. And we can also analyze some more results here. These are not the part of objective, but I just want to mention. See, these when you click on the performance, you can identify how with the length of the reactor the temperature was changing, how the pressure was changing, how different variables were changing. You can also click on the plot, and on the x-axis in the plug flow reactor you will always find that there will be a length of the reactor. As you can see that the temperature was high in the start, then start to drop, and then it achieved a steady state condition. And similarly with the temperature of the utility fluid, it remained almost a constant. If I want to understand how the pressure was changing, there was no change in the pressure in the reactors, and this is what we can also assess from our feed and the product pressure 162 in the kilopascal in the inlet and 162 at the outlet. And other analysis you can perform, you can see how the enthalpy was changing with the length of the reactor, how there was a drop in the entropy with the length of the reactor, and the duty here is important. That's what I want to bring your attention. Because it is an adiabatic reactor, this duty will remain 0, and how the vapor fraction was changing, it is almost 1, means it was all the vapors here. Now let's close this, and we can also analyze some results. You can see with the flow, how the with the length of your tubular reactor, how the molar flow was changing. You can just click on plot, and this is the molar flow. You can also identify how the mass was changing, how was the change in the volumetric flow, and your heat transfer. These are the reaction details. We can also plot them. What you need to do, you need to just select it, any required type, and click on, let's say I want to see for acetone. This is for my acetone, how the ketone was doing in the reactors, and the methane. So these are all different colors. You can also change their color of the legends if you want. So for now, let's say this is my blue, and we can make some different colors. So, and the same is we can also correlate how the viscosity changes were happening, how the mass density along the length of the tubular reactor was changing, and how was the composition changing. So as you can see that this is for let's check the legend here, acetone. So the acetone composition was decreasing, whereas for ketene, which is in the blue, and the methane, which is in the green. So what happening, we have the maximum concentration of the reactant, and as soon as the concentration of the reactant start to decrease, the concentration of the product start to increase, because the product started to form at these points. And of course with the length of the tubular reactor or the plug flow reactor, the concentration of the reactant was decreasing and the concentration of the product was increasing, because the reactant acetone was converting into products. So at one point we have there is a point here where we have achieved complete conversion of the reactant into our product. In our next lecture we will see for with the catalyst how quickly we can have this conversion achieved. But for now, these are some of the objective. The last objective in our statement is calculate the residence time of plug flow reactor. How we work on this? So we need to bring in our object palette here, and we need to bring in our spreadsheet. Now this spreadsheet is very much similar to what you are doing in Microsoft Excel. However, there are some differences. I will explain you those. So you double click on a spreadsheet, and we don't need anything from this one. Just click on spreadsheet here, and here you just need to type in about the calculations parameters. So the first is I need to know what is the reactor volume. The second you type is as a liquid flow rate, and the third is the residence time. In the column B, we need to identify what are their values. So how we work on it, just right click on this, click on add import variables, and choose your reactor name. In my case it is PFR 100, and find out what is the reactor volume here. This is my reactor volume. Click on this, click on add, and now click on done. As you can see that it has added the reactor volume. If you recall from our simulation, this is what we provided when we were designing our reactor, and it is also available in our question statement, which is 5 meter cube. If I take you back here, this is the value 5 meter cube. The second point is what the HYSYS has calculated for us. How do you add that? How you add that? You just click on is add import variable and click on the product and find out what is the actual volume flow. So this is, just click on actual volume flow, click on add and click on done here. As you can see, it is black in color. This means we can't change it. This has been calculated by HYSYS. In the next step, we need to provide the formula. So you put your equal sign here and you type in B1, which is the reactor volume, divided by B2 and hit enter. So the residence time is nothing, it is just the ratio of the reactor volume and the liquid flow rate. If you recall, I mentioned you that it is very similar to Microsoft Excel, but it is not the same as Microsoft Excel. The reason is that, if you allow me to delete this, let's press equal sign, and I can't correlate cell in this spreadsheet of HYSYS. So this means it is similar, but it is a little bit different. So I need to type those cell myself. So it will be B1 over B2. Residence time is 0.6302 and the units are in hours. Usually we report the residence time in terms of the minute. What you need to do, click on this cell and go here. This is your formula bar, just like in Microsoft Excel, and you need to multiply it by 60, which will convert these units into minutes. So I can say that the residence time for this reactor is 37.81 minutes. So that's how you work on this problem. I hope this helps, and if you have any questions, you can email me. Thank you.